Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. All right, let's do the Python part for module number 9, classification and regression trees card. So I'm going to cover everything we did in the theory lecture and we'll see how we can implement those things in Python. Okay, so here is where you can find the code. Go to my GitHub repository, machine learning, lectures and code, and find module number 9, card, Python. There are going to be 2 notebooks here, and one for decision tree, one for classification, one for regression. So I'm going to go in details for the classification one, and regression one is going to be pretty a simple extension to that, right? We're going to just use different class, but everything else is pretty much the same. So I'm going to go over the classification first. So if you go ahead and click on this open in Colab, the link should work. And just make sure that you fetch the repository, you have the latest version of these notebooks. So I can go ahead and run this in Google Colab. However, I want to do it on my local computer using VS Code because, again, I love working with GitHub Copilot, so that's why I prefer coding in VS Code, especially when the data set is small or I can use packages locally on my computer. So just like any other Python part for this lecture series, I'm gonna implement decision trees both in using Scikit-Learn from scratch and PyCaret at the end of it. So without further ado, let's do this. So these are the files, classification and regression. So I have it in my VS Code, and I'm gonna go ahead and just let it run. So let's select the kernel. I have the PyCaret environment already installed. So with the PyCaret package, basically Scikit-Learn is there too, so you don't need to install it separately if you have PyCaret already installed. So I think typically for structured data machine learning, PyCaret is good enough, but feel free to use any kind of package that includes Scikit-Learn or directly work with Scikit-Learn. All right, let's start with importing the relevant libraries, NumPy, Pandas, Matplotlib, and Seaborn for visualization. We're going to ignore the warnings, set the random state to 1000, read the dataset from my GitHub repository. We have seen this dataset before, there's nothing new here, but every single time I will teach you something new, right? The dataset is the same, but for example, sometimes I teach you how to impute using linear regression. Sometimes I teach you how to do one-hot encoding or label encoding. So this time I will walk you through to something called label encoding. So this is probably new to some of you guys. And then we're going to talk about why we can do label encoding instead of one-hot encoding when it comes to decision trees. So if you have watched the theory lecture, you already know the answer because decision trees can handle the categorical variables more efficiently. So that's why we're going to work with simple labels instead of one-hot encoding for each category. All right, so here's a data set. We have gender, male, female, age, estimated salary, and this is our target variable if somebody is going to purchase an SUV or not, right? Again, we have seen this data set before. We have done some EDAs on it, and then we discussed the details. But very simple data set with 400 rows, and then pretty straightforward, nothing missing there. Because this is a classification task, as I told you earlier, I typically want to look at the crosstab, basically look at the balance of the labels, right? So I'm going to use crosstab function, and I will pass. If you pass one variable, it's going to show basically the cross tabulation for that same variable. But you can use this crosstab for multiple variables as well. Okay, so I'm going to normalize it and then multiply it by 100. It means that these numbers are percentage, right? So now it means that 64% of the data is no purchase, 35% is purchase. So it is pretty. Well, it's roughly balanced, so that means that what is implication? It means that we can use accuracy, AUC, ROC, and things like that. So, all right, pre-processing the data. Again, the data set is already cleaned and there's no missing values there. I can go ahead and drop the user ID right away because we're not going to use it. However, remember, we have categorical variable called gender. From the theory lecture, we know that decision trees are able to handle categorical variables, but not if they're string. So the model cannot handle the string variables, so we have to turn them into numbers, right? So if those categories are ordinal, we can use ordinal encoder. If they are not ordinal, we can use something called label encoder. So for example, we can label male as 1, female as 0. So let's see how we can do it in Python. Okay, so that's the intention. So this is basically what I told you to just here as well. So feel free to pause the video or just use a notebook to read these things. The idea is that we can do label encoding, one-hot encoding, or ordinal encoding. So one-hot encoding is basically used for all the machine learning models, but decision trees, again, are able to handle those categorical variables. You don't need to, for example, imagine you have zip codes, and then what if you have 1,000 zip codes? So if you want to do one-hot encoding, so it's going to create 1,000 extra dimension. So that's the downside. So that's why just working with categorical variables as ordinal encoded one, it's a lot better. Reduce the dimension of the data by a ton, or keep the dimensionality low. But on the other side, when you're doing label encoding, you're assuming that there's some kind of relationship between different categories. That might not be necessarily the case, right? If you do one-hot encoding, you assume that those vectors are orthogonal to each other, right? So for example, you have a category of color, so green, red, blue, and then you're assuming that green and red and blue are orthogonal to each other. They're completely independent. But if you do label encoding, for example, if you label them as 0, 1, 2, the model might pick up some relationship, which is not necessarily what you want to do that. So you should be careful. But again, because it's reduced the dimensionality of the data, we would definitely want to give it a try. In this case, it's only gender, male and female. It doesn't make a huge difference, but we will see later on that again, if you have lots of classes for a categorical variable, it will be a lot better if you do label encoding. Okay, so label encoding, we're going to import it from pre-processing module, Scikit-Learn. It's called label encoder. So this is a class, and we're going to create our own object. So this is our encoder. I call it label encoder. You can call it anything. And then I can say, here's my object. Go ahead and fit transform, right? So fit transform, because I'm going to apply to the entire data, I will do fit transform. So this means that it's going to use the entire data set, find the parameters, and then transform the entire data set as well. So the idea is that take the gender column and then fit transform it from male and female to 1 and 0. So 1 is male, 0 is female, right? So I'm gonna go ahead and create a new variable. By the way, you can look into the classes of that encoder object. So did I not run this? Probably not. Okay, so here are the classes. So for example, classes is female, male. When you see something like this, you know that, okay, the order is 0, 1. If you want to change the order, so you have to put it in the fit one, but just check the documentation. It's pretty straightforward. Or use ChatGPT or Bard to help you with that kind of thing. So again, it's pretty straightforward. All right, so here I'm gonna go ahead and create a new variable, call it male, because it's more intuitive, right? If I leave that variable as gender, then you have to read the documentation or the data dictionary. What does 0 mean? What does 1 mean? But if I change it to male, now it makes perfect sense. If the variable name is male, so 1 means male and 0 means female. So that's why I'm gonna go ahead and create this one. And if I look at the head of the data set, now we have and I want to do it in 2 steps to just make sure that this encoder is doing the job correctly. So I'm going to keep the gender for now, just compare them. So male, male, female, female, male. So 1, 1, 0, 0, 1. So it's doing its job. So I'm going to go ahead and remove that gender from the columns. Okay. And I can go ahead and reorder the variable name. So this is typically good if you want to do some visualization, if you want to do the correlogram or the pairwise pair plot or things like that. The reason it's useful is that because when you have the target variable at the very beginning or at the very end, then these graphs, it's a lot easier to read them, right? So I'm going to go ahead and bring the target variable, which is purchase, at the beginning. And then if you look at the head of the data, now we have purchase and other variables, exponential variables or features. Okay, we can do correlation or correlogram. And now this is going to show me the correlation between purchase and all the variables. So I need to only look at this one column and I'm done with that, right? So if you're a male, the correlation is negative, you're not going to get an SUV. It's not going to get, it's basically, it's negatively correlated, right? And correlation doesn't mean causation for sure. So this is basic econometric. But the idea is that if anything, it's capturing linear relationship, right? So between purchase and age, it seems that the higher the age, the more correlation between purchasing an SUV, and the higher estimated salary, the higher odds of getting an SUV. So something like that. You can read the correlation like this, but be careful. This is just showing you the linear relationship, not necessarily the nonlinear. So I think I've discussed all these things back in module 3 when we did the econometric approach of linear regression. All right, so we can do a pair plot as well. Again, this data set is very low dimensional. And because it's low dimensional, I would love to do pair plot to just give me more insight, right? Because, for example, when I look at something like this, then I know that this data is begging for a nonlinear classifier. Look at that. We have estimated salary and age. And if I can have a nonlinear decision boundary like this, it's going to do a perfect job, right? So again, this is going to give you some rough idea that what models should perform better. So for example, if I say something like this, I'm not going to do logistic regression, the basic logistic regression as a classifier. So I will do either, for example, polynomial logistic regression, penalized with some, I don't know, some regularization, or I would do KNN, or now I know that I can do decision trees because it's perfectly suited for a task like this. All right. Then we can go ahead and do our regular splitting stuff. So the target variable, everything but the purchases as a feature, we're going to split it 20% test, 80% train. So here's the head of the train set, and now we can go ahead and do the rest of the pre-processing. Do we need to scale the features? The answer is no, because decision trees, basically, they're making decisions by splitting the nodes based on the absolute value of features, not necessarily the scale version of that. And we're not calculating any Euclidean distance metric here, so we're good to go. We don't need to scale the features. But if you do that, it's not going to hurt, so don't worry, you can go ahead and scale the features as well. I think in the pros and cons, we talked about all these things, so if you watch the theory lecture, you get more insight. So here's the decision tree classifier, and honestly, the difference between this notebook and the regression is just this line, right? And the data set is different. Of course, the task is regression, but there we're going to import decision tree regressor. Now here we are importing decision tree classifier. That's pretty much it. And the documentation is actually, it's very, very well documented. Let me go ahead and open the Scikit-Learn documentation for this. We can do Sklearn documentation for decision tree classifier. Okay, something like that. And then the first link. So this is a documentation. So here are the parameters. We have criteria, splitter, max depth, mean sample split, and all these good stuff that we have talked about in very detail in the theory lecture. But at the very high level, remember the criteria can be Gini, entropy, log loss, or by default it's Gini. We can change it to entropy. So these are going to be the hyperparameters that we can play around with if we want to tune this model, if you want to make it better. Right, the splitter, so this is, we can, by default it's going to be left as best, or we can do random splitting, or we can just search for the best one, right? Go all the way down to the tree and find the best one. Max depth, I think this is the depth of the tree, which we already are familiar with. Mean sample split. So this is the minimum number of samples required to do the split, right? I'm going to show you an example later on in the notebook that say, hey, for example, imagine you want to, at each node, you want this minimum number of observations in order to make a split. If it is less than that, just stop there, terminate the tree, right? Something like that. And with that concept, so these are kind of regularization concepts, right? You know, regularization parameters that help you to control the growth of your tree. This one, max depth, is obviously one of them. Mean sample leaf, the same story. Mean weight fraction leaf, max features. So the max feature for decision tree, we're not going to play around with it, but when it comes to putting a bunch of these trees together, when we talk about random forest, we're going to play around with this one a lot more. But basically, what max features is doing is that when you want to make a new split down the road in the tree, you have to decide how many of the features you want to use. You want to use all the features, and that's what by default it's doing. It's, when you leave it as none, it's gonna, for each split, it's gonna use all the features. So for example, here I have 3 features: age, estimated salary, and what was the other one? Gender, yeah, male. It's gonna, for down the tree, for each split, for making a new decision on each split, it's gonna look at all these 3 features, right? We can work with a subset of features, the squared value. For example, if I have 9 features, if you use SQRT, it's going to use, at each split, it's going to use 3 features. We can do the log 2 version. We can, yeah, things like that. Again, for random forest, I have some set of slides for that. We talk about these max features in more details. Random state is just a random initializer, random number. Max leaf node, again, this is another regularization parameter, or just help you to control the bushiness of a tree. Minimum impurity decrease. So again, these are pretty straightforward, right? So for example, you want to make sure that I need to have at least this amount of decrease in impurity to justify the next split, right? Class weight, if your data set is imbalanced, I think we talked about this one in the logistic regression and KNN as well. It's the exact same story. And you can work with a balanced version of the data, right? So inversely related to the frequency of the observations. And this is the one that we're going to talk about a little in detail, which is CCP alpha, right? Cost complexity pruning alpha. So I think on the slides, it was slide number 24. So I'm going to talk about this one in detail. So when we look at the Python code. So we're just for now, let's keep it there. And then when we get there, I'll explain it. All right, let's go back to the Python part. So here are the parameters and hyperparameters that I just covered. So again, feel free to pause the video or just look at the notebook. And then we are going to go ahead and create our classifier. So I'm going to go ahead and call it tree_classifier. People sometimes call it CLF, standing for classifier, but again, I just want it to be just more informative. Call it tree classifier. We exactly know what we're talking about. So this is a class from what we imported up there, right? So decision tree classifier. So once you have an object, you can go ahead and train it. So I use the fit module to model or attribute to train it. Use it, train it on the train set, right? So now the tree has been trained. I have an object which is trained. So off of that object, I can call many good stuff here. So if I do tree_classifier dot, so these are all the things that you can do. You can look at the number of classes. You can see what are the features, number of outputs. You can make predictions. You can look at the score, which is accuracy in this case because it's classification. You can change the parameters. You can look at the tree itself, right? So we're going to look at this one as well. So for example, this is, if I do .tree_, now I can look at the max depth. If you do another dot to show you what are the options, you can look at the max depth, max number of classes, and etc., right? So I'm going to go ahead and show a bunch of those things to you. So for example, if I do tree classifier get parameters, it's going to give me the default parameters that's set for the classifier. So the default parameters are these things. Alpha is equal to 0. It means that you make sure they have the bushiest tree ever. And then later on, we're going to use cost complexity pruning method to prune it back. Class weight none, criteria Gini. So these are the default values, max depth. And as you can see, there's nothing restricting this tree, right? It's going to say at the very basic, go ahead and train the bushiest tree ever you can, right? And as you can see, for example, mean sample leaf is equal to 1, mean sample split is equal to 2. So it means that at each, for example, at each node leaf, you have at least one observation, which is very intuitive, right? And if you want to make a split, of course, you need to have 2 observations. So these are the default values. And we can say, again, we can do .tree_ and then .max depth, extract the maximum depth. So as you can see, this tree with 3 simple features is going all the way down to the depth of 9. So this is crazy, right? So it means that we can have 2 to the power of 9 terminal nodes, but how many actual terminal nodes we end up with? We can look at that one. But if you look at the node count, so 93 in this case, right? If you use a get depth, it's going to tell you the depth of the tree as well. So this is just a function you can use or method you can use, right? So again, different ways to extract same information. All right, so now we can go ahead and make some predictions, right? So if I say, hey, the object .predict, I want to make some prediction on the test set. These are my y-hats. And remember, y-hats are going to be a bunch of 0, 1s, right? So if I do y-hat, it's using that threshold 50% to classify, right? So if the prediction is less than 50%, call it 0. If it is greater than 50%, call it 1. Where is these percentages coming from? Because remember, in decision trees, when you're doing classification, at each terminal node, we're basically calculating probabilities of each class at the bottom of each terminal node, right? So I think if it is a little confusing, watch the theory lecture. We talked about it in very detail. All right. Like any other probabilistic model, the output can be probabilities as well. So I can say tree classifier, give me the predict probabilities, right? And this is going to give me the probability of class 0 and class 1. So I'm going to extract the probability of class 1, which is the second column, right? And this is Python. Second column means number 1. Okay, and I can look at these probabilities, and you might wonder, why these probabilities are very close to 0, 1. Because remember, this tree that we are training here is super bushy, goes all the way to the depth 9. This is overkill, I guess, and you're going to see that why it's overkill. It's overfitting in the train set for sure. And because with a simple data set like this, we don't need to go all the way to the 9th level and then 93 kind of nodes. And then that's why the probabilities are going to be close to 0, 1 here. Actually here they are 0, 1. So basically means that a terminal node, it's pure classes, right? So we go all the way down the tree, and then at each terminal node we have either class purchased or no purchased. That's it. That's why we are going to see a bunch of 0, 1s here. Later on, I'm going to tune the parameters or hyperparameters. We come up with an optimal tree, and in that optimal tree, these numbers are not going to be 0, 1. It's going to be just probabilities, right? All right, so we can look at the histogram of the probabilities, and as you can see, it's spread it out between 0 and 1. All right, so next we can look into some performance metrics. So let's go ahead and import the ones we are going to use: accuracy score, recall, precision score, F1 score, and then we can do some built-in classification report. This is what I really like to work with. And yeah, so pretty straightforward. I think by this time in the course, you should be familiar with all these things. So that's, if you think that I'm a little going fast, so make sure that you follow along from very first Python lecture. As we move forward, I speed up. I try to talk about new stuff, not repeating myself. Okay, so here is the confusion matrix. Good numbers, 44, 18, bad numbers, 4 and 14, right? True positive, true negative, false positive, false negative, right? So, and then we can look at the classification report. So this is doing a decent job. So because the data set is almost balanced, I like this number, 78%. And remember, this is performance in the test set, right? And we already know that this model is overfitting in the train set because it's super bushy, and we need to prune it back, right? So let's talk about that pruning process. So this is pruning the tree using cost complexity pruning method, right? So basically we're going to choose alpha with cross-validation. So there's this built-in function in Scikit-Learn, which is called, it's a method, right? If I have an object, classifier object, off of that object I can do cost complexity pruning path. And this is going to give me two things, right? First of all, I have to say, use the train set and go ahead and calculate this cost complexity pruning path for me and save it as a path. And this path is a dictionary. Let me actually run this code. You see, I'm showing the path here, and path is a dictionary. The first key item is CCP alpha. So these are the alphas, and the second one is impurities. I can go ahead and save them. I say save all the alphas and call it CCP underscore alpha, and then save all the impurities. So if I do path dot, again, this is a dictionary, I can do dot to extract the key items. So CCP alpha and impurities, right? So let's see, how does this work? Because this is typically a little confusing for a student. So let me try to explain it in simple language. So these CCP alpha, first of all, each alpha is corresponding to an impurity, right? So if alpha is equal to 0, we are not imposing any restriction on the tree. We can say, go ahead and work with the bushiest tree ever, because let me pull up the, so this is the cost function for the regression, but for the classification, so here we have classification. It's going to be pretty much the same. Just instead of mean squared error, we're going to work with cross entropy, right? But the penalization part is there, right? So here, if alpha is equal to 0, we can say there's no restriction on how far you want to make that tree big. So that's the idea. If alpha is equal to 0, and then we can go ahead and calculate an impurity for that. If alpha is equal to this number, then there's an associated impurity for that, right? But where are these numbers coming from? Are they set or are they calculated? So the answer is that alpha is kind of reverse engineered. We are going to go ahead and calculate these numbers instead of setting them, because ex ante, you have no idea what is alpha, right? So how does it work? It's like this, you know, we have to say, let me see if I can find a tree. Yeah, here's a tree. So I'm going to go ahead and use the entire tree, right? And then calculate, imagine this is classification. Oh, interesting, what's going on? Yeah, let's see if it's working. Yeah, it's working. Okay. So I'm going to use the entire tree and go ahead and calculate the Gini or entropy or cross entropy, right? And then I'm going to go, so this is, and whatever that number is, I'm going to say, hey, that's corresponding to alpha is equal to 0. Then I'm going to go ahead and let's say cut this node, right? Cut this node, it means that we're going to combine these two terminal nodes to one node and then recalculate the cross entropy, right? And the difference is going to be a representation of this alpha that we have, right? Because remember, you're going to find a number for this summation, and then you can back out because you have number of t. This is, depending on what kind of tree you're working with, you can figure this out, and then you can back out the alpha. So that's why I say alpha is not set, it's calculated, right? And the good news is that you don't need to do it manually. So this has been already done in Scikit-Learn. And then now you can borrow these alphas and then run it through a for loop, do cross-validation, and see which alpha is the best, right? So basically, which alpha gives you the best combination of variance bias, right? So that's what we're gonna do. So hopefully it was clear. Please make sure you read this explanation. This is basically what I walked you through. Okay, so then we can, so what's the goal now? Now say, hey, I have a bunch of alphas. And then I'm going to go ahead and put it in a for loop, do cross-validation, find the best alpha. So this is going to be my best hyper parameter for alpha, right? So again, these are our alpha, CCP alphas. And we have seen something like this for KNN, or we did exactly something like this for KNN. So this is pretty much the same. So I say for alphas in all these 20 alphas, so because I have 20 here, go ahead and calculate the cross-validated version accuracy, right? So cross-valid score, estimator, decision tree, my CCP alpha is different for each value of CCP alpha, right? My alpha is different for each value of CCP alpha. And train it on a train set, use 5-fold and scoring accuracy. So, and then go ahead and append these things to your accuracy cross-validation. I'm gonna put it in a nice table. And so now we have different values of alpha and different values of cross-validation accuracy, right? So we can plot it. There you go. So it seems that our accuracy is maximized here when alpha is some number. So we have to back it out. It's hard to read it like this. So that's why we're going to use argmax. So what is the argmax of this output? Remember, this is the output data frame, output accuracy cross-validation. So argmax is going to happen in the 15 elements. And what is that 15 elements? So I have to say index location 15th and give me the columns. So alpha was equal to 0.0051 and accuracy is 0.89. So with the maximum accuracy we can get if we use cost complexity pruning method is 89%. So this is great, right? Remember, if we didn't prune the tree, which I told you that was overfitting in the train set, the best accuracy we got was 78. Now in a test set, right? Now we are getting something cross-validated version. We're getting to 89, which is a lot better. So this is a less overfitted tree for sure. Okay. So this is one way to prune a tree. Another way is that you go brute force and say, you know what, the max depth of the tree should be 4. That's it, or 3. All right, so I'm gonna back out. I'm gonna save this alpha and call it alpha optimal. So this is what we're doing, optimal alpha. And again, so I'm gonna save this number. And now I'm going to retrain the decision tree with the optimal alpha. So I'm going to call this object optimal decision tree. Oh, sounds good, right? And then I train the model, make some prediction in a test set. And with that, I can go ahead and look at the F1 score, recall, precision, you name it. But a good thing is that we can see for this optimal tree, what were the optimal parameters, right? So if I do get parameters, it's going to tell me, hey, for this tuned or pruned tree, here are the parameters. Alpha is equal to 0.005 and max depth none. It doesn't mean that the depth of the tree was the unlimited, it was restricted by alpha. Actually, I can find that depth. If I say optimal DT, so I can do either get depth or I can do _3, right? Optimal, yep, max depth is going to be 4. So as you can see, without doing cost complexity pruning method, the max depth was 9. Now the max depth is 4, which is a lot smaller, right? So this means that at most we can have 2 to the power of 4 or 16 terminal node compared to 2 to the power of 9 terminal node, which was insane. Okay, so and the number of leaves reduced from, I think it was 21 up there, 93 up there. Now it's only 8, which is, yeah, great. So we can visualize this tree as well. We can do the confusion matrix for the optimal tree. Again, these numbers are better. We can do the classification report. Again, we get 86 compared to 78%. So your cost complexity pruning method is just working. And then we can use cross-validation to estimate this number, for example, right? Remember, this is the performance in the test set. If you want to estimate the performance of the model in the test set, you have to do cross-validation, and that's what I'm using here. So I'm gonna use train set and then to do 5-fold cross-validation, take the average of accuracy and report a number for this 0.86. Report the estimated number of that. So again, we have done this many times before in the semester, so you should be pretty confident here. Again, I'm creating this cross-valid score, and the score is going to be accuracy because the data set is balanced. If it was imbalanced, I would have used F1 score. We're going to have 5 of them because this is 5-fold. I'm going to take the average, so 88. So this 88% is a fair estimate of the performance of the model in the test set. Pretty good. Remember, we do cross-validation for 2 reasons: tuning hyperparameter, which we already did, and estimating the performance in the test set, which we are doing now. All right, let's go ahead and visualize the tree now. Okay, for visualization, there are 3, 4, or I don't know how many different methods you can do that. I think, I don't know, 4 or 5 years ago when I was doing these things for the first time, and when I was teaching them for the first time, not using them, I had to search internet what are different ways to just visualize a tree. But you guys, you can do ChatGPT now, you can do Google Bard, and it's going to tell you many different ways to do the same job. So I'll leave this here, but if you're curious, so this is a good blog that walk you through 4 different ways of visualizing decision trees. But honestly, nowadays, more recently, I'm using less and less kind of those web blogging. I'm doing ChatGPT or let's say Google Bard, especially for machine learning if you're using Scikit-Learn, because it's heavy documented, and if you're not doing something fancy, or if you're not doing something, a cutting edge technology or a cutting edge model. So if you're using a well-developed Scikit-Learn kind of model, go ahead and trust the ChatGPT's answers. Worst case scenario, you're going to give it a try, it doesn't work, and you're going to troubleshoot it. So that's also a technique, that's also a skill that you should learn. Okay, so here I'm gonna show it the scatter plot one more time for estimated salary and age, just to give you an idea what we're discussing here. I want to do something like this. I want you to see. Well, actually, I'm gonna go ahead and work with only these 2 features, right? And I'm going to tell you that let's see what is a better split, right? If I ask you visually, what split should we use? So probably you're gonna say maybe age around to 40, right? So this is a good split. I don't know, maybe 41, and estimated salary around 90,000 ish. So as you can see, these are good splits, right? Which one should come first? I don't know. We have to go ahead. You remember there was a slide here. Let me see, where's that slide? Yeah, here we go. So which split to start with? If you watch the video, so there are going to be a couple of more numbers here, and then so for example, should I start with a split S with X1 or this split with X2? So this is the exact same question we have. We have to calculate the entropy or Gini and see which one is going to give you more information gain or reduce the impurity more, right? Yeah, but roughly we know that 41 is a good candidate, 90,000-ish is a good candidate. Let's see if that's the case. So I'm going to restrict the tree to be the max depth of 2 because I know that for this kind of classifier, I don't need a bushy tree. I need a classifier as simple as this. That's it. Maybe I need at most a couple of splits. That's it, right? So that's why I do max depth is equal to 2, and I call it simple D tree. I don't know, you can call it anything. Just retrain another tree, right? And now I'm going to use plot tree from tree module in Scikit-Learn, right? This is a built-in module in Scikit-Learn for visualizing tree. Plot tree was one method. And I can go ahead and actually plot that, right? If you run this one. So as you can see, it says, so it seems that the best split was age less than 42.5. So this is where we were close, right? And then if the answer is yes, we go to, by the way, this is Python. In Python, no, well, again, this is Python 3 visualization. Yes means go to the left, no means go to the right. So if it is less than 42.5, go to the left. So this is a yes thing, right? So less than 42, it means that we go to the left if it is yes. And then we need another split for estimated salary around 90,000, right? Hopefully you're following, right? So let's see if that's the case. Yeah, estimated salary around 90,000. So at this split, and we know that if you go down the tree, this Gini should decrease, right? Because the smaller the Gini, the more pure classes we're going to end up with. Obviously, at the very top of the tree, the Gini is going to be super large. And we know that Gini is equal to 0.5. It means complete randomness, right? So yeah, as we go down the tree, the Gini is going to improve. So here we know that estimated salary is a good one, and we said the max depth is equal to 2, so we are not going to make any further split here. So this is where we're going to end up, right? So we're going to end up with this is a, I don't know, maybe decent Gini for this class. So let's find these ones. You know, where are these 195 observations, and what does this mean? 188 and 7, right? So let's see that. So where are we? We are age less than 42 and estimated salary less than 90. So we are here. Age less than 42 to the left, estimated salary less than 9,000 to the bottom, right? So we are here, these blue dots, right? And as you can see, there are going to be, the majority is going to be blue, and then we have a bunch of orange here as well. Orange is purchased, blue is no purchased, right? So these are the ones who are younger with less salary, so they're not purchasing SUV. So let's find them. There you go. There are 195 of them. 188 ended up not purchasing, and only 7 ended up purchasing, right? So these 7s were the orange ones here. Yep, there you go. All right, so that's how you can read a tree. And this is from the theory lecture. Remember, we said that this is super interpretable, and now you see what do I mean by that. Again, you can go to the other side, and then if you go to the other side, it seems that the algorithm decides to do another cut on the age. This is interesting, right? So if age is greater than 42.5, you're on the right side. And then again, instead of splitting by estimated salary, decided to do another cut for age, which was 47-ish, which is, yeah, it's going to say, here's one region, here's one region, here's one region, here's one region. So this is what we are going to see at the bottom of the tree. We said the max step is equal to 2. So that's why we're seeing 4 terminal nodes or four regions. All right, you can save your figure as a PNG file. So this is, again, this is a Python thing. You can save a fig, and then you can just export it later. All right, so let's do a quick exercise together. What is the level? So level is what? 1, 2. Okay. What is absolute value of t, or number of terminal nodes? So what is the answer? 1, 2, 3, 4. Very good. Okay, so we have 4 of them. And how do you make sure that each terminal node has at least 50 observation, right? So here we have, look at that. For this one, we have 195, which is okay. For this one, we have 36. For this one, we have 26. For this one, we have 63. So how can I change this decision tree classifier to make sure that that's the case, right? So if you go back to the documentation, we should find something related to max. So this is mean sample. Yeah, this is going to do it for us, right? So how many samples you need at each leaf at the end of the day. So let's go ahead and play around with that. So I'm going to go back up. Mean sample leaf. Yeah, mean sample leaf as 5. Oh, well, we can. Let's you can set the random state to 1000 if you wish, but yeah, let's say. So this is gonna do the job for us. If I leave to 50, now if I retrain the model, now look at the tree again. As you can see, there you go. It's not gonna cut this side anymore, because if it does, it's gonna have less than 50 observations. So it's gonna stop right there. 50, more than 50, obviously, more than 50 here, and more than 50 or equal to 50 here. So this is interesting. So what is the depth of this tree? 2. What is the number of terminal nodes or absolute value of t? Very good, 3. 1, 2, 3. I think you got this. Okay, so let's do quick visualization, and then we're going to do the PyCaret part. So for this visualization, honestly, we have discussed this before, and now with PyCaret, you don't need to do it this way. But if you're, because again, we're reducing the dimensionality into 2 of the features only. What if you have 10 features, right? So then you use PyCaret. PyCaret is doing PCA, Principal Component Analysis. We're going to learn this later on in the course, to reduce the dimension from 10 to 2 and then visualize it. But if you want to just visualize it in 2 simple dimensions, we have to pick those dimensions ourselves. I'm going to say, let's pick age and estimated salary, retrain a tree, and the tree, yeah. We can scale the features. Again, this is not mandatory, but for visualization purposes, I'm going to scale it. So our decision boundary is going to, well, again, the scales are going to be the same, basically, if I use a standard scaler. And then here's the tree. I'm going to do max depth is equal to 2. And here's the visualization part. So again, don't worry about this code. So I think we covered it before, but don't worry about it. You can use PyCaret to just take care of this thing for you. But I have a point that I'm doing it manually because I want to play around with that max depth, right? So this is our beautiful decision boundary, which is coming from train set, right? So it means that if I remove all these dots and throw test set, this boundary is not going to change. The boundary is calculated using, so this lines, these boundaries are calculated using train set. If I apply it to the test set, that's not going to move. See? So here the max depth was equal to 2, so that's why we ended up with 2 regions at the end of the day at most, right? So was it max depth 1? I think it's 1 here. Well, or 2. So we decided not to cut any further. But what if I do max depth is equal to 10? I want to make it super crazy overfit and unnecessary complex. Look at that. So this is actually capturing all these things. So it seems that in the train set is doing a decent job. Let me actually go even more insane. So let's do 100. This is the super bushy tree, right? Obviously it's gonna overkill, right? So this is overkilling in a train set. What is the accuracy in the train set? 100%. But this is ridiculous, right? Do you see that? These things are ridiculous. Why we have a green prediction decision boundary here? Why we have red here? This is nonsense because it's overfitting to the train set. If I use this for the test set, that nonsense is going to become obvious here. So obviously this is overfitting to the train set, and it's not doing a good job for the test set. So that's why I would like to do this visualization manually. I can play around with these things. Again, this is for learning purposes. Later on, when you're an expert, you don't need to do these things like this. If you want to visualize the decision boundaries, you can use PyCaret. All right, let's go to the exciting part, which is the PyCaret. Okay. So for PyCaret, I'm going to go ahead and open the documentation. So this is PyCaret documentation, and I would love to show you the model container as well. So this is what we've been doing consistently in the past. So this is a classifier. So I'm going to go ahead and open the classification model container, and I'm going to look for decision trees. Decision trees. Yeah, this is our decision tree classifier, which is directly coming from Scikit-Learn, right? So PyCaret is directly using this thing that we learned today, right? So, and then when it comes to tuning the parameters or hyperparameters with PyCaret, just be aware these are the limitations, right? So these are the tune grid dictionary that PyCaret is using under the hood. So it means that your max depth is going from 1 to 15, not more. Your max features are these things, right? Your, again, min samples leaf are these numbers. So if you want to do anything different, you have to do it manually with Scikit-Learn. Just be aware when you're doing When you're tuning hyperparameter with PyCaret, it's limited. It's limited to its preset values, right? Okay, great. So that's all I wanted to share with you from the model container. Let's go back to the code. So just like previous times, I'm not going to run the PyCaret part because sometimes it's going to take time comparing models, or well, actually we're not comparing models here. We are creating decision trees. At the end of the course, I'm going to compare 25 different regression classification models by running one line of code. But right now we're learning them one by one. So by the time you're watching this, as the time of recording, the PyCaret is 3.1. And the dataset is the same one. I'm going to go ahead and set an experiment. From classification, I'm going to import everything. And this is how we are going to set up an experiment, right? Set up, by the way, I can call it experiment 1, and then this is my experiment 1. But if you do it that way, you have to make sure that down the road, when you're creating model, the model is coming from that experiment 1 as well, experiment 1. Okay, so this is a PyCaret 3.0 thing. In PyCaret 2.0, we didn't have this luxury of working with different experiments, right? So again, I'm going to talk about these things at the end of the semester. So here's the experiment you're setting up. So this is the entire data set. This is target variable. Features to ignore, basically user ID. I don't want to use that one. This is just random state. Let's do 70-30, train test split, pre-process true. We can just leave it as false too. Categorical variables, gender. So gender is a categorical feature. So we can go ahead and run this, and obviously it's going to tell us that there's one categorical and then 2 numerics, and that's it. This is a pretty simple data set and no fancy pre-processing. So these are available models. So we've already covered logistic regression, KNN. Now we are talking about decision trees. So this is the one that we're covering now. So it's called the model ID is DT. So if you want to create it, you have to say create model estimator DT. So I'm going to call it DT as well. So don't confuse this DT with this DT. This is the model ID. This is an object, right? You can call it something else to just avoid the confusion. So when you run this, it's going to do by default 10-fold cross-validation and report all these good numbers for you. I'm going to look into the accuracy. Average accuracy 86.79. So decision tree out of the box 86. This is pretty close to what we calculated, right? Yeah. Then we can tune this model by using tune model. It's going to go ahead and use these parameters. Remember these parameters, and do a grid search and then search for the best combination, and it's going to report it back to you. So this is, we went from 86-ish to 89-ish. So it's 3%-ish improve. Then if you're curious what was going on under the hood, so you can say, plot those parameters for me. So these are the optimal parameters if you use PyCaret. So it's going to say, CCP alpha, go ahead and work with the Bushi's tree, but I'm going to restrict it some other way. So I'm going to say max steps is equal to 10, max features 1. Yeah. Again, these are the restrictions. So for example, for whatever reason, they decided to change it from 2 to 5, right? This one from 1 to 6, right? So this is different compared to what we did using cost complexity pruning method. But regardless, the outcome is pretty much, it's a good one. It's 89% accuracy. We can do the ROC, AUC ROC. So we have done all these things before. So if you think that this is a little fast, please just understand that this is the third time or fourth time we're doing this. So I don't want to make you bored with repeating myself. So the accuracy, AUC for class 0-1, both of them good numbers, so I'll take it. And this is a balanced data set, so I trust these numbers. I can look at the confusion matrix. This is another plot. I can look at the classification report, another plot. Again, the model is doing a decent job. Look at the precision recall F1 score. And here is our threshold plot. So it's going to tell me that, there's this vertical line, this 25%-ish. This is a threshold that gives us a good combination of precision recall, F1, and accuracy, right? But if you're only interested in accuracy, just leave it as default. Your threshold should be 50%, which is, by the way, what the model is using. We can look at the precision recall graph, which is giving us 89%. So for different values of recall, on average, the precision is 89. This is great, right? So I'll take this. And we can visualize the decision boundary. And now we have feature 1, feature 2. These are not age. These are not estimated salary. This feature 1 is a combination of age, estimated salary, and your gender. So it's a linear combination of all those things. It can be linear or non-linear combination depending on if you're using simple PCA or kernel PCA. If this is too fancy, just bear with me. I'm going to cover all these things later in the course. And finally, we're going to look into the learning curve. So it seems that these are kind of converging, or the gap is there, but these are good numbers, right? The 87%, 90. So this is in a train set. We're in the 91%. In the cross validation, we're 89ish. So the gap is pretty small, but because the scale is greater than 0.8, that's why it seems large. So I'm happy with this. Should having more observation, is it going to help? I don't know, probably. If you see that these two are converging, the answer is yes. If you think that the gap is there and it's just staying there, it means that the model is not complex enough and it's having high bias. All right, so we can also look at the feature importance. So if I plot something called features, so actually I can go ahead and show you the documentation in PyCaret. Go to PyCaret, classification, plot model. There you go. These are all available plots that you can do. I'm using so this is going to show you the most important one. If you do feature all, it's going to show, if you have 100 features, it's going to list them all. Here, because we only have 3 features, it really doesn't matter. It's going to show it anyways. So for our case, it seems that age was the most important feature, then estimated salary was next, and gender, pretty much irrelevant. So all right, so that was pretty much it. So we covered decision tree classifier both in Scikit-Learn and PyCaret. All right, now let's do the decision tree regressor. So with the classifier behind us, we can easily go ahead and do the regression just in less than 10 minutes, I guess. So let's look into that. So here's where you can find the code. So if you go back to the module 9 folder, GitHub repository, decision trees regression IPy notebook. So let's go ahead and do that. So this is my PyCaret environment. You can run it in Google Colab as well. You have to install PyCaret if you want to do the PyCaret versions. But for the first half, we're going to do Scikit-Learn. So here's the data set, right? We have seen this data set before, and now we are going to apply yet another model to the same data set. We're predicting wage based on these features, right? And here we have, so for example, last time I think we saw lots of missing values for, let's see, for further education. I think last time we ended up doing linear regression imputation to just impute those missing values. But this time, we're just for the sake of simplicity, we're going to remove the further education in total, and we're going to replace the missing values from moderate education with the median moderate education. That's it, right? So again, we're going to get rid of these further education, and we're going to replace these 78 by the median value. All right, so again, if you find me that going over all these things a little fast, just be aware we have done this before. So just check out the previous Python videos. And but at the same time, I'll try to explain enough that you can watch these videos as a standalone. So moderate education, you're imputing that one with median. Okay, so again, simple splitting the data, 20 test and 80% train, and then here's the head of the train set. Scaling the features, again, this is the decision tree. We don't need to do that. So these are exact same parameters that we saw for classifier, exact same thing, parameters and hyperparameters. So that's why I say that there's nothing new here. The only thing is that so for regression, by default, the criteria is going to be MSE, which is simply, well, that's typically one loss function that we use for classification, for regression, right? So let's see. Yeah, all these things are MSE, a mean squared error. Okay. All right. So yeah, here's the difference: decision tree regressor compared to classifier. Now I have an object. I can go ahead and train that object. Let me go ahead and import it first, and then make some predictions, and then we can make a nice data frame showing the actuals versus predictions. So these are the actuals versus predictions. And it seems that the model is off. So let's see. At least with the default values of the hyperparameters of the decision tree. When I leave it blank, it means that go ahead and use the default values, right? So just like previous one, I can say, what are those parameters, right? So I can say tree, regressor, give me the parameters, right? Okay, so these are the default parameters that you're using. Your criteria is the squared error, right? Mean squared error. All right, cool. We are not putting any restriction on the bushiness of the tree now. Okay, so this is regression. You don't need to do this. Again, this is just for teaching purposes. I want to show you what's going on exactly. If I plot the actual versus predicted, if all the observations are closer to the 45-degree line, that's awesome, right? So basically it says that y and y hats are the same and your model is doing great. Here our model is doing an okay job. It's not the best one, but yeah, it is what it is. We're using decision trees for regression. And we know that just like KNN, that we rarely use it for regression, decision tree, the same story, right? Especially if the dimension of the data is large, and then because we have more powerful models when it comes to regression. And even decision tree itself, we're not going to use decision tree for the sake of its accuracy. We're going to ensemble a bunch of these trees, and later on we're going to use, for example, a model called XGBoost, which is going to do a lot better than a simple decision tree. Decision tree is there for you to understand the theory well, and then maybe if you want to interpret things, visualize a tree, and then other than that, for performance metrics, we're going to go beyond this simple decision tree. Okay, we can go ahead and report the mean squared error and the RMSE in the test set, and this is this is the RMSE in the test set. What is the unit? The unit is the same as your target variable, whatever target variable was. So the target variable was, what was it? It was wage. Where was it? Here, all the way to the top. So wage and 76,900. So this is a unit, so that's dollar. So RMSE 53,000 means that the unit is dollar. So this is important. You should be aware how you can interpret these things, these metrics that you're putting together. So $53,000. Okay. Now try max step is equal to 1. What do you expect to see? So if there's one reason I'm just talking about this decision tree regressors is this, because I want you to see what's going on. If I do max depth is equal to 1, what does it mean? It means that at most, our tree have 2 terminal nodes, right? If the tree has 2 terminal nodes, at most, how many predictions it's going to make for the regression? Here, look at that. Here we have 3 terminal nodes, right? 1, 2, 3. So it's going to make the average, take the average of all these numbers, recall it as, call it y hat 2. This is y hat 3, this is y hat 1, right? Now, if I have max depth is equal to 1, I'm going to end up with 2 regions. So region 1, region 2. So how many predictions? 2 predictions, right? It's going to take the average of all those predictions in one region and call it, for example, your prediction, right? So let me go ahead and rerun these things. And as you can see, these are all 2 numbers. 83,106, 83,106, 106,000, right? Again, there's no surprise here. And this should not be surprising at all, because your model is always predicting these 2 levels, because this is a super simple tree with just 1 split. Okay. Yeah. Now let me go back and remove that thing, because we want to do cost complexity pruning thing. So let's remove this. Let's train a very bushy tree and then use cost complexity pruning method to prune it back, right? So exact same thing as I went over the classification, the same story. We're going to import the cross-validation scorer, and then we're going to find the CCP alphas, right? Because we want to write a for loop, go over different values of alpha, and then find the optimal one, right? So I talked about it in very detail when we went over the classification. So check out the first part of the video. So cost complexity pruning path. So I have a path now. Now it means that I have CCP alpha. So I have alphas. We don't need to use the impurities, but we know what they are. So these are the alphas. I'm going to go put it in a nice for loop and see which alpha is going to give me the best combination of bias variance, right? Okay. So actually in this case, we have 619 of those alphas, and here are those values for alphas, right? So we're going to write a for loop around all these 619 using cross-validation. I'm not going to run this because it's going to take some time. So I'm just walk you through this. And what is the metric? We are going to use negative mean squared error. We have to multiply by negative. So that's why we get the positive mean squared error. And then I take the square root of that one, call it RMSE. So I'm basically calculating the RMSE for different values of alpha. Okay, where are these alphas coming from? From the CCP alpha, cost complexity pruning method. So when I run this and then visualize it, then where's the optimal value? Wherever the RMSE is minimized. Remember, this is regression. You want to minimize the RMSE. For classification, we wanted to maximize accuracy. This is minimization. So we're going to do the argmin to find this element. So it seems that this is 616th element. And then what is the value of alpha? The alpha is 4. Well, actually, it's a large number. It's 4,467. Oh, this is a super large number. Oh, it's 10 to the power 7, right? So 4.6 multiplied 10 to the power 7. Why the alpha is crazy large for regression compared to classification? It all goes back to the, let's go back to the page 24, to your cost function. If your y variable is in a scale of $1,000, so $1,000 to the power of 2, so we're talking about $1 million in terms of this mean squared error. So this alpha should be a very large number to make any difference in that cost function. For classification, because we were working with class entropy, that number is small, so your alpha can be small. So if you're ever wondering why the alphas for regression is super large, for classification is smaller, that's the case. We can have regression. Imagine you're doing interest rate, right? You want to predict some, I don't know, regression on interest rate. If that's the case, the unit is going to be small, the alpha is going to be small as well. So this alpha depends on the unit of your target variable. All right, so then this is the alpha. We can say, go ahead and create my optimal decision tree using that alpha, train it, calculate the predictions, and calculate the RMSE. So the pruned version is 39,000. Remember, the unpruned version was 53,000. So we're doing a lot better, right? So what was it? Was it 53,000? Yeah, 53-ish thousand. And now the pruned version tree is 39,000, which is great. Okay, so it's a lot improvement. All right, so we can look at the optimal parameters as well. So visualization, the same story. So we can visualize a tree. And then here it seems that we start with IQ. If your IQ is less than 101, we go to the left. If it is greater than 101, we go to the right. Then the next best variable to start with is hours, where we put the split 31. Then the next one, if it is less than 31, go to the left. If it is greater than 31, go to the right, and etc., etc. And obviously the scored error is going to decrease as we go down the tree, right? Okay, so let's see. Okay, so here this is the visualization for regression, and remember, for regression this is color coded. I have two features, IQ and hours. The darker it is, the higher the wage, right? And as you can see, it's not even for us as human, it's hard to put a clear cut split either for IQ or hours. So that's why probably the model is having a hard time with this regression, right? But anyways, you know, whatever it is, the optimal decision tree was start with IQ 101. So starting with IQ 101. So if it is less than that, call it something. If it is greater than that, go search for other splits. Okay, cool. And now we can see the regression lines as well. And if you want to do that, so this is again just for the sake of teaching purposes. In practice, you don't need to visualize these things. But I'm going to show you something. I'm going to say, you know what, go ahead and create a decision tree with the max depth is equal to 1 and only use one feature, because remember, I want to visualize it. This is your X, this is your Y, right? So to only use that one feature. Here I decided to pick IQ because IQ was the most important feature based on this decision tree. We started with IQ. That's for visualization. I'm going to use that one. And say, hey, this is IQ, this is wage. Go ahead and show me the line of the decision tree. And this is how it's going to look like. If the depth is equal to 1, I'm going to have 2 of them. Let me actually run this. This is fun. If the depth is equal to 3, I have 2 to the power of 3, at most 8 different numbers. At most. Does it always 8? Probably not, right? So here 1, 2, 3, 4, 5, 6, 7. We have 7 different numbers here, right? Why? Because it seems that we don't need to have 8 terminal nodes. We can have any number less than 8, right? So this is basically that visualization. Again, last but not least, let's do the PyCaret thing. The PyCaret is pretty straightforward. We're going to import the data. We're going to pre-process it. And yeah, nothing fancy here. So the target variable is going to be wage, and everything else we're going to use it. So let's set up the experiment. Look at the models. This is our decision tree. Should be somewhere. No, DT. Yeah, decision tree regressor. And there you go. We can create that. I call it DT underscore reg. So this is our decision tree regressor to just make it different from the classifier. And if I look at the RMSE, this is 52,000. This is pretty close to what we got. 52,700 we got. This is 52,800-ish. And we can tune this model if we can do any better. And the answer is yes, absolutely. We went from 53,000 to 38,000. This is pretty much close to those numbers that what we got. And we can plot the parameters. So these are the optimal values. We can plot the residuals, the normality of residuals. Again, we talked about these things in the econometric part as well. We can look at the learning curve. So here, the learning curve is actually screaming at us that give me more data because it's converging like decently. And then if we have more observation, there's a chance that the cross-validation score is going to get higher and higher, which is the R-score, by the way. The default value of a score in regression is R-squared. All right. And by the way, we can, for classification, we could do that too. For regression, we can use PyCaret, plot model, plot is tree. And this is our tree. Okay. Cool. And finally, we can look at the features, right? So from plot model, just plot the features. And this is the interpretability part of decision trees, which I really like. So we're going to talk about these things in random forest and XGBoost as well. So yeah, it seems that for our wage prediction, education is the most important feature. Not surprisingly, that's why you're learning these things, right? Education matters. Otherwise, why are we doing this? It matters for your wage, for everything, right? So then IQ is next, age, hours, tenure, father education, mother education, etc. So these are the least important ones. So the most important ones, education. All right, that was pretty much it. Hopefully you enjoyed it. Until the next one, take care.